Everybody, welcome back to another fun and exciting geometry class. Today, we are going to be on page number 95 and 96, and that is lesson 2.19, Proving Quadrilaterals Are Parallelograms. Now, what I have on the screen here is I have the theorem number, and then I have a quadrilateral, and we're going to talk about three different ways today that we can actually prove a quadrilateral is a parallelogram. So let's talk about just kind of a little definition. What is a quadrilateral? Well, a quadrilateral, there we go, has four sides. And that's the definition. A shape, a closed shape with four sides. So you are looking at a quadrilateral on the screen. It has four sides. It's a closed shape, which means it's a quadrilateral. Now, what are parallelograms? Well, parallelograms are quadrilaterals, but specifically that means the word parallel is in there, and so it means that they have parallel sides. So this side is parallel to this side, and this side is parallel to this side. That's a parallelogram. Now, you're going to be asked in later exercises to prove that those are parallel or parallelograms. How do we prove that? Well, theorem number 21 kind of starts us off in the right direction here, and it says if the opposite sides of a quadrilateral are equal, then the figure is a parallelogram. So in other words, if let's say this side right here, okay, what's opposite of this side? Let's call these, let me just label these. I'll call these just like they do in your book, A, B, C, and D. Okay, so what we need to do is we need to prove that AB, we'll start with AB, is equal to CD. AB is equal to CD. If we can prove that, then we are on our way to proving that this is a parallelogram. The second one that we would have to prove is that AD is equal to BC. So if we can prove those two things, if we can say, okay, AB equals CD, so if we can prove this one, AB is equal to CD. And see, here's the thing. Not only do we have to prove that, because let me show you what we could get. We could get, okay, parallel lines, or let's say we could get equal lines. And then we could have one line be equal and one line not be equal. Well, that's not even a closed shape, okay? So in geometry, we always had to prove like the extreme, prove it like people don't know anything, and so the extreme would be we have to close the shape too, because it has to be a quadrilateral in order to be a parallelogram. So in order to close that shape, we would have to make sure that these outside lines are equal as well. If we can prove that AD equals BC, then we can prove that this is a parallelogram. How do we know that? Well, the reason why we know that is because this line on top and this line on the bottom are being constrained or being limited by these lines on the side. And these lines on the side are being limited by these lines on the top and the bottom. They're all working together to limit the other ones on how far they can go, what the distance is. And once you prove that, once you prove that they're equal, you also prove that they're parallel. This goes back to last lesson when we proved that parallel lines with the same length lines in between them are equal. And it doesn't matter where you put these. As long as they're equal, then this would all be equal, and then this would be your parallelogram. Okay, so that's kind of based on the parallel lesson that we did. I think it was 2.18. No, 2.17, the distance. So that's based on those distance and parallel lines. All right, so Theorem 21, let's review it real quick, is if you have two sides, opposite sides. Now, don't forget it says opposite sides. So the opposite of CD is AB, and the opposite of AD is BC. So if you have two opposite sides that are equal, and you have two other opposite sides that are equal, then the figure is a parallelogram. So if the opposite sides are equal, then you have a parallelogram. Theorem 21. All right, next, Theorem 22. Theorem 22. It says, if two sides of a quadrilateral are equal and parallel, then the figure is a parallelogram. Now, you might be thinking, wait a second, didn't we just have that in Theorem 21? No, it's a little different, and here's what's different about it. It says, if two sides, so now if we go around and we label this A, B, C, D, and we're only talking about two sides. So let's take this side, AB and CD. Okay, so we're just going to take those two sides. So if we can say that AB equals CD, AB equals CD. Now, do we have a parallelogram right now? Maybe, maybe not. Because remember, I showed you in the other one, if we took this and we said, well, what if we had just a little short line right here? Well, if AD does not equal CB, BC, then we don't necessarily have a parallelogram. So what else do we need to prove in this one? In the last one, we proved that AB equals CD, and we proved AD equals BC. So on this one, we're proving the same thing to begin with. We're proving that AB equals CD. But now look back at theorem number 22 on page 95, and it says, if two sides of the quadrilateral are equal and parallel, So if we can say that AB is also parallel to CD, we don't have to do anything with those ones. If we can just prove that AB and CD are equal and parallel, then we can prove that this line is going to attach. This line is going to make the quadrilateral be a parallelogram. Let me show you one other thing. What if we have AB? Let me show you a shape here. We have AB, and we have, well, let me move AB down here a little bit. So we have AB, and we have CD. And let's say those are equal. So A, B, C, D. Do we have a parallelogram? The answer is no, because those are not parallel. So when we go to connect these, we're going to find that that shape is not a parallelogram because CD is not parallel to AB. So that is one of the prerequisites, at least in theorem number 22, to proving just another way. These are two different ways to prove. So if we prove that AB is equal to CD and AD is equal to BC, that works. Or if we prove that AB is equal to CD and that they are parallel to each other, then we also prove that it is a parallelogram. Okay. The third way is on page number 96, and this is theorem number 23. Theorem number 23. And it says, if the diagonals of a quadrilateral bisect each other, then the figure is a parallelogram. So if we take our diagonals and we draw our diagonals on here, and if we can prove that this point right here in the middle, draw a point here in the middle, that this point right here, this guy right here, is the bisector of these lines. Okay? Is it bisecting those lines? If it is, or if, in other words, this piece equals this piece, and this piece equals this piece, then by definition of a parallelogram, it is a quadrilateral and it is a parallelogram by the very definition of a parallelogram, because parallelograms have equal diagonals when they're bisected, and that's the kind of part of the definition of the actual parallelogram. So in the first one, we're proving two sides, or actually the opposite sides. In the second one, we are proving that two sides are equal and parallel. And here in the third one, we're not dealing with the sides at all. We're dealing with the diagonals. So if you can prove that the diagonals, when they're bisected, they create equal parts, then you would have a parallelogram. All right. And I believe that's it. Yeah, it looks like there's just some exercises to kind of help you practice on that, those different ideas there, but that is the basis of lesson 2.19. All right, hope you learned something today. We'll see you later. Bye-bye.